Today we are going to discuss the transition element lesson. So far we have taken the properties of those transition elements, just we have completed. Today you are going to see one more property, that is oxidation state. So today we are going to discuss about the oxidation state of a D block element, that is 3D, 4D, 5D and 6D series. So first we will start with the what are all the oxidation states possible for a 3D transition elements. We know 3D series, there are totally 10 elements. One is, if you take scandium, another one is titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc. Okay, there are totally 10 elements are available. If you take the oxidation state of each element, the oxidation state of each element is different. There are some common oxidation states are possible for this. That is, you take for scandium. Okay, if you take for scandium, the possible oxidation state for scandium is only +3 possible. Okay, and if you take for titanium, the possible oxidation state is +4, +3, +2. For vanadium, if you go with +5, +4, +3 possible, +2 also possible. For chromium, +6, +5, +4, +3, +2 state is possible. For manganese, if you go with +7, +6, +5, +4, +3, +2 is possible. Okay, and if you are going with iron, +6 possible and +3, +2 is possible. So if you go with cobalt, +4, +3 and +2 is possible. So if you are taking nickel complex also will get +4, +3, +2 oxidation state. And the copper we know +2 and +1, there are some common oxidation state. And if you take zinc, only +2 oxidation state available. Okay, these are the oxidation states available for different 3D transition element. Okay, now when we take an oxidation state of this 3D transition element, all the transition element except scandium and zinc. Okay, so except scandium and zinc, all remaining element shows a variable oxidation state. Remaining shows variable oxidation state. Okay, so if you take scandium, only +3 is available. If you take zinc, only +2 is available. But for all remaining elements, we can expect the variable oxidation state. And what is the reason for this variable oxidation state? We know that the general electronic configuration for a D block element is the outer electronic configuration n-1d and ns orbital. Okay, so the variable oxidation state, the reason for that, if you take these two orbital, there is a small energy gap. There is a small energy gap available between these two orbita. So that is understood. From that we can get one point. For a compound formation, those two orbitals can involve. For a compound formation, this two orbital can involve. That shows that if you want exhibit a metal with a +2 oxidation state, means only the electron from the s orbital can be removed. Suppose if you are going with a higher oxidation state, a metal can be, that is electron can be removed from the n-1 d orbitals. Still further going on, removal of electron from the d orbitals possible. So for a compound formation, both the orbital electrons involved. So from that you will get 1 point. Okay, and next in the lower oxidation state, for simple compounds, metal formed a complex, okay, that complex simple oxidation state can be obtained by the removal of a 2 electron from the ns orbital, whereas higher oxidation state you have to remove the electron from the n-1 d orbital. Okay, this is the reason for the 3D transition series element. Some of them except scandium and zinc, remaining all the elements exhibit variable oxidation state. Okay, and what are all the observation from this oxidation state, what we can make? That is some few points you have to remember to write the from the oxidation state of the metal. Okay, what are all the points? So first one, all the transition element shows the common oxidation state +2 except scandium. All elements common oxidation state +2. So except scandium. Except scandium. This shows that 1 point we can eliminate the electron only from ns orbital electron. Okay, for scandium we can expect only the removal of only 3 electron. Okay, all element common oxidation state +2, but except scandium. So from that we can take the stability of the n-1 d orbitals. Okay, the n-1 d orbital stabilities can be increased after scandium. Okay, the common oxidation state, what all the element except scandium is +2. So from that 1 point is revealed. So n-1 d orbital stabilities can be increased after the scandium. So that is nothing but after scandium only n-1 d orbital electrons can be used for the formation of a compound. Okay, and second one. So if you are taking that the oxidation state, for example, if you are moving with the scandium to titanium. So let me write the electronic configuration for scandium, outer electronic configuration 3d1 4s2. 3d1 4s2. The number of d electrons available only 1. Okay. So let me write for titanium 3d2 4s2. The number of d electrons available only 2. So at end of the series and in the middle, suppose if I am taking the middle manganese 3d5 4s2. 3d5 4s2. That shows there are totally 5 electrons available in the d orbital. So if I am taking at the end of the series like copper 3d10 4s1, it shows that d orbital electrons 10. Okay, from this point what we expect is at the beginning of the series, okay, at the beginning of the series, the oxidation state is going on increasing. So, the oxidation state of any metal, okay, it is related or it is depend on the number of the d electrons available. So, the oxidation state increases, okay, when the number of unpaired electron, that is number of unpaired electron increases, number of unpaired electron increases. Okay. So now I will explain. First you will take a scandium. Only one unpaired electron. So only one possible oxidation state available. For titanium, 2 unpaired electron, little bit increases. But in manganese there are 5 unpaired electron. So maximum oxidation state you will get for maximum +7 to +2. So next is copper. So here copper, the availability of the unpaired electron decreases. So if I am taking for manganese, there are 5 unpaired electrons. That's all over. Again for iron, you will get 1 electron here. Again for cobalt, nickel, like that, copper, it is going on increasing the paired electron. So the paired electron increases, the oxidation state decreases. So the number of unpaired electron increases means oxidation state increases. Okay. Number of paired electron increases means oxidation state decreases. So that's why at the beginning of the series, the fewer element exhibit the oxidation state a little bit higher, going on increasing. Middle reaches the highest value, and at the end of the series, the oxidation status decreases. Okay, so this is a point we should get for regarding of all transition element. Okay, and next third one, if I am taking a zinc alone, if I am taking zinc, the electronic configuration 3D10 4s2. Okay, why zinc is getting only +2 oxidation state means you can remove only these 2 electron from the ns orbital, not electron from the d orbital. Why? The d orbital is completely filled, stablest electronic configuration. So we can remove only the electron from the s orbital. So that's why zinc is getting only +2 oxidation state. Okay. And next one, if I am taking the transition element, that is the maximum transition element, the maximum oxidation state transition element. Transition elements forms compound with only fluorine and oxygen. That is, the maximum oxidation state transition element forms compound only with fluorine and oxygen. Why means this fluorine and oxygen, because of the small size and high electronegative value. Because of the small size and high electronegative value. I will explain by taking an example of potassium dichromate. Okay, potassium dichromate. The oxidation state of chromium is +6, highest oxidation state. This highest oxidation state transition element forms complex with the high electronegative element oxygen. So here I can expect the oxidation state here, the potassium monovalent, so 2 + 1 plus 2x plus 7 into for oxygen minus 2. So you will get 2 plus 2x minus 14. So 2x minus 12 equal to 0. So x equal to +6. Okay. So the maximum oxidation state of transition element forms compound only with fluorine and oxygen. So just I have taken one example, potassium dichromate. You can take the oxide form of a manganese also as a best example. For manganese exhibit +7 oxidation state. Okay, this is maximum oxidation state. Next, fifth point. So the metal, if I am taking metal from the transition element, okay. Metal, if I am taking the metal with the transition element formation of a complex, just I am explained. So next, if I am taking middle element, okay, middle element is manganese. So manganese shows the oxidation state, increased oxidation state, where we will expect +2 to +7, where I can remove all the electrons, okay. So how it is possible? So I can explain with the number of the d orbitals available. So if I am taking the scandium to copper, just we are taking middle manganese element, okay. So while I am moving from scandium to manganese, so you know already from that scandium only 1 d electrons available, and from the titanium only 2 d electrons available. If I am taking manganese, 5 electrons available, and last there is no availability of a d electron. Okay, so here if I am taking scandium alone, so 3d1 4s2, the scandium shows only 1 electron. That means this 1 electron is available to share or lose. Okay, this 1 electron orbital only available for the formation of a compound. Same if I am taking manganese 3d5 4s2, there are totally 5 unpaired electron, okay, and same in the middle we are expecting more oxidation state, and at the last copper, if I am taking copper 3d10 4s1, so here 3d10 like this, there is no availability of the d electrons. Okay, so what is the point? It is clear. Starting of the series, okay, the number of availability of the d electron is low, 1 2 3 like that. In the middle, the number of availability of the d electron is completely, that is off-filled configuration, and at the end of the series, copper and zinc. So you will get all the 3d electrons are completely filled. So if I am taking before series, like before copper, nickel, if I am taking nickel, 3d8 4s2. So where I can expect 3d d containing only 8 electrons. Okay, now I will compare here. The availability of a d orbital electron only less. Here the availability of the d electron also less. So from that you will get 1 point. When the number of availability of a d electron is increases, okay, increases means oxidation state also increases. So from the scandium, the number of availability of an electron is only 1. So the oxidation state is less. In the middle, availability of the electron is 5. So that should be more. At the end of the series, the availability of the d electron is less. So that's why nickel also decreased in the oxidation state. So the oxidation state slowly increases, in the middle reaches the maximum value, and then it slowly decreases, okay, based on the number of the d electrons present in the orbital. Okay, next we will see the transition element in lower oxidation state. In lower oxidation state forms ionic compounds, whereas transition elements in higher oxidation state forms a covalent compounds. Okay, these are the 2 points you have to remember. Lower oxidation state, it forms only the ionic compound, whereas in higher oxidation state it forms a covalent compounds. Okay, and next we can see about, okay, maximum oxidation states or stable only for heavier elements. Maximum oxidation state are stable only for heavier element. Like for example, if I am taking molybdenum in the oxidation state is 6 and tungsten in the oxidation state 6. These are more stable than chromium 6. So molybdenum in the oxidation state of 6 and tungsten in the oxidation state of 6, that is higher oxidation state, are more stable than chromium, that is also in higher oxidation state is 6. And even though it is molybdenum and tungstens are more stable, we are not using as a stronger oxidizing agent. But chromium in the form of potassium dichromate. We know already potassium dichromate, the oxidation state of chromium is +6. Chromium is in the oxidation state +6. So this potassium dichromate act as a strong oxidizing agent. Oxidizing agent in acidic medium. Even though it is not stable, comparing with the molybdenum and tungsten formed complex, but the chromium 6 compound, it is acting as a strong oxidizing agent in what medium? Means acidic medium. So maximum oxidation state stable compounds for heavier elements, that is an example. Just we are comparing molybdenum with the chromium compound. Okay, and next, if you are moving with the that is D block transition element, we are going to read about the relative stabilities. So I can expect the stability of a compound, stability of the compounds. First one, depend upon half and fully filled orbital. Okay, like I will give an example. If I am taking manganese in the form of +2 oxidation state, you can take, and manganese in +3 oxidation state. Let me explain Mn+2 and Mn+3. In manganese, a general electronic configuration, outer electronic configuration 3d5 4s2. So this is 3d5 and 4s2, 2 electron. For Mn+2 oxidation state, where I can remove the electron from the s orbital, so that's why we will get 3d5 only. So 4 is 0, so 3d5 means only 5 electrons, 4 is 0. Next, if I am taking Mn+3, again there is one more chance of removal of a 5th electron. So 3d4 possible. So 3d4 means the number of unpaired electron only 4. Okay, so I can compare the stability of the compounds here, which is more stable. Okay, based on the half-filled electronic configuration in D block, that is a manganese compound 3D series, the D orbital contains 5 unpaired electron. So manganese Mn+2 state is more stable than Mn+3, that is stability. Okay, that is stability. So the stability of the compound can be determined on the basis of the half and fully filled orbital in d electron. But in manganese Mn+3 there are only 4 unpaired electron. Okay, even though unpaired electron increases, we are not getting a stability. That's why Mn+2 is more stable in Mn+3. Again one more. So based on that, that is if you are taking an element with two different oxidation state. Like for example, if I am taking copper, so copper exhibit two different state. One is Cu plus and Cu plus 2. It is in plus 1 oxidation state. The copper 2 plus is plus 2 oxidation state. The transition element with a different oxidation state, in that case the stability of that metal ion is determined based on the electrode reduction potential. Electrode reduction potential, where I can explain how it is formation of a copper plus 2. You know already. Copper means we'll expect 3D10 4s2. Okay, so D10. So where you'll get 3D10 like that, S2. Okay, so if I want to remove Cu plus 3D10 4s1, so where we let one electron in the s orbital. So copper plus means where you can remove only this one, so 3D10 only possible. Okay, and Cu plus 2, where I can remove only the 10th electron, so we'll get 3D9, so we'll get 9. Okay, one unpaired electron. Okay, now how it is reduced? So if I am adding copper plus, if I am taking copper plus, okay, so if I add one electron, that will be reduced into copper. That electrode reduction potential, okay, electrode reduction potential, where I can give you 0.52 volt. Okay, 0.52 volt. And Cu2 plus, it is reduced by getting 2 electron, it is reduced into copper. Okay, that is Cu plus 2. How you are going to reduce? That is electrode reduction potential value will be 0.34 volt. Okay, and based on that Cu plus and Cu plus 2 comparison, Cu plus 2 is more stable compared with the Cu plus. Okay, Cu plus 2 is more stable compared with the Cu plus based on the electrode reduction potential value. Okay, and next comparing Cu plus 2 and Cu plus, which will be reduced easily, means Cu plus is readily reduced. So from that electrode reduction potential, which ion is more stable, we can explain by taking a different oxidation state of a copper plus 1 and plus 2. Okay, next low oxidation state. How it is possible? Low oxidation state. Okay, a transition element forms a complex with a ligand like CO. You will expect the low oxidation state. For example, you will take nickel tetracarbonyl, that is nickel tetracarbonyl and iron pentacarbonyl, iron pentacarbonyl. Okay, so here you will expect nickel and iron in zero oxidation state. Here the CO acting as a pi acceptor. So in addition to that sigma bonding, this effect is called a synergic bonding. So in addition to that, we are adding the pi acceptor character. So that's why the oxidation state of a nickel and iron shows a 0 oxidation state. And next, the oxidation state depends on the nature of the solvent. That is, what are the effect of nature of solvent? Okay. For example, if I am taking Cu plus ion, that will be unstable in water. Okay, where Cu plus is oxidized, you will get Cu plus 2. That will be stable in water. So, the oxidation state also depends upon the nature of the solvent. So, here we are using solvent as a water. So, I have explained with the two oxidation state, copper plus 1 and plus 2. Okay, so far we have discussed only the oxidation state of a 3D transition series. So, if I am taking 4D and 5D, so the 4D and 5D, the common oxidation state exhibited for like yttrium and lanthanum, you will get plus 3 common oxidation state. Plus 3 common oxidation state. If I am taking one more, the osmium, okay, osmium and ruthenium, you will get plus 8 oxidation state. Okay, in 3D, 4D and 5D transition series, lanthanum, that is yttrium and lanthanum shows plus 3, the common oxidation state, and the maximum oxidation state exhibited by osmium and ruthenium. So, in 3D transition series, the maximum oxidation state exhibits only by the metal manganese, but among all the D block elements, the maximum oxidation state shown by only osmium and ruthenium, that too plus 8. So, from that we will get one more point. Whenever in the transition series on moving down the group, the oxidation state increases. Moving down the group, the oxidation state, the stability of the higher oxidation state increases, while that of lower oxidation state decreases. So, this is evident from the one diagram called Frost diagram. That is a diagram drawn between del G0 against oxidation, okay, against oxidation number value. Okay, from that Frost diagram you will get one point, that is the common oxidation state or thermodynamically more stable oxidation state for scandium, titanium and vanadium is only plus 3. Okay, and for iron, both plus 2 and plus 3 are equal, common, more, okay, are equal. But copper at thermodynamically more stable, thus they are given only plus 1 oxidation state. Okay, and today we have discussed only the oxidation state of a transition element, that to 3D, 4D and 5D transition element. Just you keep it one point. The lower, first starting the oxidation state, it is gradually increases. In the middle, it reaches the maximum value, and then finally it decreases to the minimum value based on the number of the d electrons available. Okay, thank you.